From the creation of the universe to the power of nuclear reactions, binding energy is a fundamental concept that plays a crucial role in understanding the behavior of matter.
Whether you're exploring the mystery of atoms or the forces that hold our world together, binding energy is a key player in the drama of physics.
In this report, we'll delve into the fascinating world of binding energy, examining its origins, properties, and implications for our understanding of the universe.
Good day everyone, I am Precious Kelly Layub.
Jenny Roluna.
Angelo Quijano.
And I am Nianel Jimenez, and today we will discuss and interpret the graph of binding energy per nucleon versus mass number graph to assess the relative stability of the nucleus.
Our objectives are to 1. Explain and interpret binding energy per nucleon, plots in terms of nuclear stability and energy charges. Number 2. Compare the BEN of a nucleon in the nucleus to the ionization energy of an electron in an atom. Number 3. Use Einstein relation E(mc²) to calculate energy changes.
As you can see, this is the table of the spreadsheet of the elements, hydrogen up until to bismuth.
So as you can notice, yung nagawang spreadsheet namin is yung Z, which is stands for the atomic number, increasing. The values are increasing. While A stands for the atomic mass, which is the standard, which is used in the periodic table, is also increasing, as well as mass per unit. So as you can notice, some of those were increasing. All of them are increasing actually. While on the other hand, binding energy starts with negative. So kung papansinin ninyo, yung H, naging negative siya sa binding energy. Then, yung iba, nag-increase. However, nung dumating sila sa element na Te hanggang Cs, bumagsak yung number, which is nag-fall siya sa negative 4,589.342.72. Then, nag-increase siya into 1,085.36517. Sometimes, nag-negative siya kapag mas mataas yung atomic mass sa mass unit. Kaya siya nag-negative. Papansinin ninyo, paiba-iba yung number. May mag-i-increase, may mag-decrease. So, ganun yung na-discover namin when we use spreadsheet to compare yung mga energy charges or energy changes sa mga elements na from hydrogen at up until bismuth. So, let's now proceed to binding energy. So, sa table na to, nag-start ulit siya sa negative, which is negative 0.51. So, kung mapapansin ninyo, nag-increase and nagde-decrease. So, para rin siyang binding energy na may mag-negative, may magpa-positive, may mag-increase, may magde-decrease din. So, that's normal kapag yung atomic mass is mas mataas kaysa sa mass unit. Kasi dun, 'di ba, yung mass unit siya yung ginagamit sa yung mass unit yun yung ginagamit pang minus para makuha yung mass defect, 'di ba? So, ganun.
So, Here is the first graph of binding energy versus atomic number. Sa x-axis, nakalagay kung what kind of elements ang dinedescribe, while sa y-axis, yung mga numerical values. Kung mapapansin ninyo, ay unti-unting tumataas ang graph. However, when the graph reaches the elements tellurium, xenon, cesium, nag-decrease ng negative.
Then after nun, the graph finally increases and kung mapapansin minsan, nagpapalit-palit ang mga value, minsan negative and positive. Thus, the graph of binding energy versus atomic number typically shows a curve with a characteristic hump shape known as the binding energy curve or the nuclear binding curve. The binding energy is the amount of energy required to separate the nucleus of an atom into its individual protons and neutrons.
Overall, the binding energy versus atomic number graph provides important information about the stability and properties of atomic nuclei and is essential for understanding the behavior of nuclear reactions and nuclear energy production.
Let us now move on sa second paragraph, which is binding energy per nucleon versus atomic mass. Sa x-axis nakalagay if what elements ang dinidescribe, while on the other hand, y-axis ang may mga numerical values. If you will notice, the graph of binding energy per nucleon versus atomic mass shows a characteristic hump shape similar to the binding energy versus atomic number curve.
Kung papansinin, ang values ng atomic mass ay continuous lang sa pag-increase, while the binding energy per nucleon are sometimes increasing or decreasing. Remember that nuclei with lower atomic masses have lower binding energies per nucleon because they have fewer nucleons, while nuclei with higher atomic masses have lower binding energies per nucleon because the strong nuclear force becomes less effective at larger atomic masses, and the repulsive electromagnetic force becomes stronger.
Overall, the binding energy per nucleon versus atomic mass graph is another way to visualize the stability and properties of atomic nuclei and can provide important information for understanding the behavior of nuclear reactions and the production of nuclear energy.
For the last graph, pinagplot lang namin ang mga standard value na nakalagay sa module. This consists of the values Z, A, binding energy, and binding energy per nucleon.
Next, we will compare the BEN or binding energy of a nucleon in the nucleus to the ionization energy of an electron in an atom. The binding energy per nucleon or stands for BEN of a nucleus refers to the energy required to separate a nucleon or proton or neutron from the nucleus of an atom.
On the other hand, the ionization energy of an electron in an atom is the amount of energy required to remove an electron from an atom in its gaseous state. In general, the BEN of a nucleon in the nucleus is much higher than the ionization energy of an electron in an atom.
This is because the nucleons in the nucleus are held together by strong nuclear force, which is much stronger than the electromagnetic force that holds electrons in an atom. The strong nuclear force is responsible for binding protons and neutrons together in the nucleus, and it requires a lot of energy to overcome this force and separate a nucleon from the nucleus.
In contrast, the ionization energy of an electron in an atom is typically much lower than the binding energy of a nucleon in the nucleus. This is because the electrons in an atom are held together by the electromagnetic force, which is much weaker than the strong nuclear force. As a result, it requires less energy to remove an electron from an atom than it does to separate a nucleon from the nucleus.
Overall, while both the BEN of a nucleon in the nucleus and the ionization energy of an electron in an atom involve the breaking of atomic bonds, the energy required for each process is significantly different due to the different types of forces involved.
The last objective. Our group were glad that we were able to use the Einstein equation to be able to observe any changes a graph. We hope that you learned something from our group, and that's all. Goodbye.